A single stuck gauge let a storage tank overfill through the night. The vapor cloud that escaped ignited and engulfed more than 20 fuel storage tanks, and about 2,000 people were evacuated from their homes. We are looking at the exact anatomy of this disaster through the lens of the official Buncefield Major Incident Investigation Board Final Report, Volume 2A. The incident at the Hertfordshire Oil Storage Limited, or HOSL depot, injured 43 people. Astonishingly, given the sheer scale of the destruction, there were 0 fatalities. Acting on emergency service advice, roughly 2,000 people were evacuated from the surrounding area. The blast wave and the inferno that followed caused immense damage to nearby commercial properties, specifically the Northgate and Fuji businesses, along with residential homes located primarily in the Dacorum district. The board's strict chronological breakdown of the disaster follows these 6 key areas. 1. The incident and evacuation. 2. Timeline of the overfill. 3. Vapor cloud and ignition. 4. Technical and system failures. 5. Loss of secondary containment. And 6. Investigation findings and recommendations. Section 1. The incident and evacuation on the 11th of December, 2005. To understand the scale of the failure, the board starts with the initial event parameters. The report is very direct about the physical scope of the ignition. Quoting from page 9, at 0601, the first explosion occurred, followed by further explosions and a large fire that engulfed over 20 large storage tanks. By 0608, an emergency services major incident was declared. The resulting fire burned for several days. It emitted massive clouds of black smoke into the atmosphere that dispersed right across southern England. At the peak of the emergency response, there were 26 Hertfordshire pumps on site, 20 support vehicles, and 180 firefighters actively battling the blaze. Section 2. Timeline of the overfill during the evening of the 10th of December. The forensic timeline reveals a slow-moving disaster unfolding over several hours, centering entirely on Tank 912, inside Bund A at the HOSL West site. At 1900, Tank 912 began receiving unleaded motor fuel from the T/K South pipeline at a steady rate of 550 cubic meters per hour. For hours, everything appeared normal. A midnight stock check was carried out, and when it concluded around 0130, no abnormalities were reported. But by 0300, the automatic tank gauge failed. 2 hours and 20 minutes later, at 0520, Tank 912 was completely full and the overflow began. At 0538, closed-circuit television footage captured vapor starting to flow out of the northwest corner of the bund. Finally, at 0601, the first explosion tore through the facility. Page 9 of the report documents the precise moment the monitoring systems failed to detect the danger. It states, from approximately 03.00, the level gauge for Tank 912 recorded an unchanged reading. However, filling of Tank 912 continued at a rate of around 550 meters cubed per hour. The automatic tank gauge, or ATG, is essentially the primary fuel level indicator for the operators. Because it froze, indicating a static level at about 2/3 full, it remained safely below the threshold that would trigger any control room alarms. This silent failure allowed the steady influx of unleaded petrol to proceed completely unnoticed for hours. Section 3. Vapor cloud and ignition and its topographical spread. Once the tank overflowed, the unleashed petrol didn't just pool harmlessly on the ground. It physically manifested into a massive, volatile cloud. Page 9 establishes the exact mechanism of this vapor formation, stating, from 0520 onwards, continued pumping caused fuel to cascade down the side of the tank and through the air, leading to the rapid formation of a rich fuel/air mixture that collected in Bund A. Tank 912 was fitted with a deflector plate intended for fire-cooling water. The overflowing fuel hit this plate. While some of the fuel channeled onto the tank wall, the rest fragmented into tiny droplets. The fuel running down the wall then struck a structural wind girder, detaching and creating a second cascade. This process, known as aerodynamic fragmentation, rapidly turned the liquid fuel into a highly explosive vapor. Meteorological data from Northolt confirmed that atmospheric conditions were calm, stable, and cold. The air temperature was -1.7 degrees Celsius with 99% relative humidity. This atmospheric stability was classified as Pascal Stability Category F, meaning highly stable air with virtually no turbulence or wind to disperse the gas. Because of this cold, still air, the heavy vapor cloud was trapped at ground level. It thickened to a depth of 2 meters by 0546. Driven by gravity, the cloud flowed off-site near the junction of Cherry Tree Lane and Buncefield Lane, following the ground topography directly into the uncongested spaces of the Northgate and Fuji car park. Section 4. Technical and system failures, specifically the high-level switch. The weather explains the cloud's formation, but what about the safety systems designed to prevent the spill? The board deconstructed a critical sequence of mechanical failures. The primary fail-safe mechanism is defined on page 40 of the report. The ultimate high-level switch is, quote, part of the system to prevent overfilling of the tank, an independent mechanism which should be triggered when the specified maximum capacity is reached to cause an alarm and shut down fuel supply. Simply put, this was the ultimate emergency brake. When triggered, it's designed to send an alarm trip signal to the British Pipeline Agency, which should then close the relevant pipeline manifold valve, feeding product into the facility. The catastrophic failure of this failsafe is confirmed on page 9. Evidence suggests that the protection system, which should have shut off the supply of petrol to the tank to prevent overfilling, did not operate. Because this single ultimate high-level switch failed to activate, no shutdown signal was ever transmitted to the British Pipeline Agency. The pipeline operators were left completely blind to the unfolding disaster, and the delivery of unleaded motor fuel continued unabated. Page 6 provides the digital footprint of this failure. Examination of the valve positions shown by the ATG database confirmed that the inlet valve to tank 912, which was connected to the BP petrol manifold, was open at the time of the incident. Furthermore, records indicate that approximately 7 minutes before the ignition, the flow rate directed to tank 912 sharply increased. It jumped from 550 to 890 cubic meters per hour, drastically accelerating the cascade of fuel in those critical final minutes before the blast. This situation compounded immediately upon ignition. As page 11 outlines, the loss of the pump house, probably from an internal explosion of vapor that had entered from the surrounding cloud, immediately rendered inoperative the firefighting provisions for the site. The fire pump house provided the means to distribute cooling water for the entire Buncefield site. It was located immediately adjacent to and downhill from Bund A. Identified as a likely source of early ignition, its destruction meant the very first blast entirely disabled the on-site emergency response infrastructure. Section 5. Loss of secondary containment and environmental contamination. The failure of containment infrastructure allowed for massive off-site pollution, leading to the designation of the event as a major accident to the environment. Containment relies on layers of defense. Primary containment is the tank itself. Secondary containment is the concrete bund wall surrounding the tank. Tertiary containment involves the site boundaries and drainage systems, designed to catch anything that escapes the bund. During firefighting operations, 786,000 liters of foam concentrate and 68 million liters of water were applied to the site. The intense heat caused severe damage to the secondary concrete bunds, which led to an extensive loss of tertiary containment at the site boundaries. Massive amounts of contaminated firewater and fuel escaped off-site, ultimately compromising local groundwater and surface water. The structural limitations of the secondary containment are documented on page 6. While the bunds substantially remained standing throughout the incident, their ability to fully contain the fuel and firewaters was lost as a result of the explosion and subsequent fires. The sealant utilized in the construction and expansion joints of the concrete panels was completely destroyed by the heat. Plus, the concrete panels forming the floor of the bunds underwent significant heave. The extreme hydraulic pressure and severe fire damage literally caused the concrete floors to warp and buckle upward, destroying their ability to hold liquid. The blast damage assessment quantified the extreme physical force of the event. Standard vapor cloud explosions in uncongested environments are generally predicted to produce overpressures between 20 and 50 millibars. However, the current best estimates of the overpressures that actually occurred in the Northgate and Fuji car parks were between 700 and 1,000 millibars. The actual blast was up to 20 to 50 times more powerful than expected. Even at 2 kilometers away, the overpressure decayed to between 7 and 10 millibars, which was still enough force to shatter windows in local homes. The scientific anomaly regarding this extreme force is plainly stated on page 7. The magnitude of the overpressures generated in the open areas of the Northgate and Fuji car parks is not consistent with current understanding of vapor cloud explosions. The investigation noted that the exact mechanism for generating these unexpectedly high overpressures in a relatively open environment requires significant further research. The sheer force of this disaster broke the existing scientific models of how vapor clouds behave. Section 6. Investigation findings and recommendations focusing on system redesign. The board's findings targeted deep root causes across equipment design and safety protocols. Page 10 identifies a critical mechanical vulnerability in the equipment. It states, further investigation into the design of the ultimate high-level switch indicated that the position of a test lever or plate fitted to the switch is critical to ensure continued effective operation. This was a silent vulnerability. If a maintenance worker tested the system and accidentally left the test lever or plate in the wrong position afterward, the entire failsafe was physically disabled without triggering any warnings. Following this discovery, the competent authority issued a safety alert and improvement notices to manufacturers, requiring revised instructions on their safe use, setting, and maintenance. The board also set out specific directives to overhaul the industry's safety culture. They essentially demanded that high-hazard operators stop working in isolated silos and start sharing data. They directed the sector to collate incident data on high-potential incidents, including overfilling and alarm system defects, and to conduct thorough root cause investigations when safety-critical elements fail. By developing shared sector-wide incident databases, the fuel storage industry is mandated to draw on cross-sector innovation. Specifically, they need to take advantage of the stringent risk control experiences already utilized by the chemical processing, offshore oil and gas, and nuclear processing sectors. The fundamental directive of the investigation is established on page 11. The occurrence of a massive fuel vapor explosion confirms the overriding need to ensure the integrity of the primary means of containment. In other words, to make sure that liquid does not escape from the vessels in which it is normally meant to be confined. It is a seemingly simple directive. But as the Buncefield report proves, when the layers of protection designed to ensure that simple fact are allowed to silently degrade, the consequences will rewrite the science of industrial disasters. What other silent vulnerabilities are currently sitting unnoticed in critical infrastructure, waiting for a single stuck gauge to align with a calm, cold morning?